So, hi all, my name is Ghassan Karami. I'm a new professor here at RUP. It's my great pleasure to welcome you to this CASA distinguished lecture on privacy-friendly presence and proximity tracing. The talk will be recorded, will last until 1 o'clock in the afternoon, and will be given by Dr. Wouter Lueks. Wouter is a postdoc at EPFL in Lausanne. He designs and works mostly on privacy-friendly systems and has worked on several such systems in the past, including IRMA for anonymous authentication, including data share network, which works kind of on a document search system for investigative journalism. And he's more recently started to work on digital proximity and presence tracing systems, which will be probably the focus of the talk today. Wouter, it's great to have you here. Thank you for being here, and the floor is all yours.
Thank you so much, Ghassan, for the invitation. I hope everybody can hear me well, can see me well. It's a pleasure to be here and talk about some of the work that I've been doing. Since this talk is virtual, right, you all know that makes things a little bit more tricky. If you have any pressing questions, please drop them in the chat. I try to keep an eye out for people that scream help. I don't know where you are. Please come and rescue me, right? So please do that if you feel the need to that. Any other questions, I'll try to take at the end. So without further ado, right? So as Ghassan said, I'm Wouter Lueks. I'm a postdoc at EPFL, and really my research interest is doing research around building blocks for privacy-friendly systems, and then really I'm interested in solving real-world problems, and that requires a combination of a couple of things. So I'm interested in building systems that have very strong security and privacy properties, much stronger than your typical system that you would expect other people to deploy. And part of that strong privacy property is that I typically want to limit these systems to do one thing and one thing only, and not be relatively easy to repurpose for other, let's say, less benign applications. And then finally, because I'm interested in solving real-world problems, I have a strong focus on designing systems that can actually be deployed. Now, as Ghassan was saying, I have been doing this in a couple of contexts already that I just want to briefly highlight. So I worked on the IRMA projects, which tries to really do anonymous authentication online, think of as a replacement for passwords, and that brings with it a whole new bunch of challenges. We have been working with the International Consortium of Investigative Journalists, who you might know from, for example, the Panama Papers, to build a document search system for their journalists with very strong security and privacy properties. And then more recently, I have been actively collaborating with the International Red Cross to build systems that will help them provide aid to beneficiaries in a privacy-friendly manner. And sort of a true thread through all my research is that looking at real-world practical problems almost guarantees me that I'm finding new interesting research problems to work on. Typically, the requirement to be deployable requires the development of new cryptographic primitives or new system architectures, because existing systems just really don't fit so well with the scenarios that I'm looking at. Now, to make that a little bit more concrete, in the rest of this talk, I will actually be talking about, as Ghassan said, about systems to help with the COVID-19 pandemic. And I've been very heavily involved in this, both from the academic side as well in collaboration with app developers and the Swiss government here in Switzerland, in order to both design these and then deploy them. And as we'll go through this talk, we'll see that both of these are actually a relevant aspect to these, and both of these sort of flow back into design of these systems. So during this talk, I will actually be looking at two of these. So the first one is the one that hopefully you all have in your pocket, as part of the Corona Warn app in your case, an app that tries to detect proximity to COVID positive people, and then when that proximity is triggered, to send you a notification, right? And typically, you probably have all heard of this, but if not, I will come back to that in a few minutes. These systems use Bluetooth beacons in order to determine proximity. So that's one system that we'll be talking about. Now, the other system came up a little bit later from the realization that, yes, close proximity is a great way to get infected with COVID, But even if you're further apart, as long as you're in sort of the same enclosed space with not a lot of ventilation, you might still get infected. So really there's a need to extend these systems to also work in that type of scenario. So those are kind of the two true threat things that we'll be talking about. And whenever I work on these systems, whenever I try to work on this type of privacy-friendly systems, I roughly follow this following methodology. And none of this should come super as a surprise to you, but we'll see how these interact and how these make for interesting, challenging research problems. So first off, when you start off doing these projects, right, you need to figure out, okay, what really is the thing that we should be building? Like, what is really the problem that we have to solve? So if you think about sort of your standard software engineering terminology, these would be like your functional requirements. Now then, based solely on what the system has to do, we can already identify some security and privacy risks that stem from this, right? If you know that you need to do contact tracing, maybe you know that the system embeds some social relations between people, for example. Then finally, we just, quote unquote, design a system that tries to minimize these risks. And then finally, once you've designed the system, you try to deploy the system. Now, if this sounds very much like a waterfall type of development, you're right. And indeed, this does not really work so well. So I drew in a couple more arrows to show you really how these things interact much more in practice. So first of all, and let me enable this pointer so that you can actually see what I'm pointing at. It might be that once you identify security and privacy risks based on your functional requirements, you decide, crap, that is really something that we don't want to be building at all. It might also mean that when you're talking with people, you need to use knowledge of what is actually possible in terms of designing privacy-friendly systems to kind of drive this conversation and to ask, but what about if we do it in this slightly different way that people might not have thought about, but will actually largely address that problem as well. Now then, when you start actually designing a system, then of course the way you design that system will then bring new risks that you need to take into account. Same for when you deploy the system, right? When you deploy a system, you might again, like your deployment choices might again influence new risks. And throughout this talk, we'll actually see examples of each of these 5 green arrows here. The last one that I didn't talk about yet is that sometimes your deployment scenario puts new constraints on your designs. And this is what you see very often when I try to think, okay, this problem is actually not so difficult because I can take this off-the-shelf piece of crypto, or I can take this off-the-shelf systems building block and I can just put it together and solve it, except I typically hit these deployment constraints here. So that is roughly the outline that we're going to be following for the rest of this talk. So let's talk about functionality first. So when we were called early in March 2020, really there was, the world was on fire, right? Manual contact tracing was completely overwhelmed, couldn't keep up with the cases. And even if they kind of could, they knew that they were missing a lot of cases because people would just not be able to remember who they were 5 days ago. So that is sort of from the technical process side of view, why there was an ask to deploy technology to help with this. But this was not the only aspect that played a role here, right? Another important aspect was just sheer political pressure. Please do something because these lockdowns are horrible. Nobody wants to be in a lockdown. And by the way, if you're very liberal, this is also bloody damn expensive. And then finally, especially in Asian parts of the world, which got hit by the pandemic a little bit earlier, they were already rolling out apps. These apps were not particularly privacy friendly, but at least they were doing something. So the question for us was, okay, can we build a system that helps with mitigating this COVID-19 pandemic? Now, just as a very quick reminder, what is this contact tracing thing that I'm talking about? I'm assuming all of you know, but just to make sure that we're kind of on the same page. So what manual contact tracing tries to do is that whenever you identify a positive person through testing, you will then try to identify all the people that they might have infected. And then tell these people, okay, either please get tested yourself or at least quarantine so that when this person quarantines, they cannot be infecting other people. Now, typically, the way this works in manual contact tracing, right, is somebody calls you and says, okay, can you please list me all these people? Can you also please provide their phone numbers and other contact data? And then this glorified call center will try and reach all these people, right? This is slow, and this also doesn't particularly work well if, for example, this person cannot be identified. Now, if you were to ask this first question that I started out with, right? What should this digital system do to help with pandemic mitigation? A very typical answer that you might get is actually not what we in the end ended up building. And the reason why is that there is a tendency, and I've seen this over and over again, when you ask people what should we do, there is a tendency to digitize existing processes. So in this case, they might say, what would really help if we have an automatic way to get names and addresses of contacts, because then at least we don't need to gather all of these. Now, what I want you to notice is that this thing really is not the underlying problem that these systems are trying to solve. Really, the underlying problem is, if you wish, try and slow down the spread of the pandemic by making people quarantine or get tested. So after a lot of back and forth with both contact tracers and epidemiologists, we actually slightly turned this on its head and said, okay, really what would be a good thing for these digital contact tracing systems to do is instead to automatically notify people that were close enough and long enough to this positive person to have been at risk of getting infected with COVID-19. And notice that changing this to notify has two effects. One, me putting on my privacy hat, this is a little more privacy friendly. It also is more efficient in the sense that it doesn't require call center members to call a lot of people. Now, it also has downsides, but this is what we settled. Okay, so we have our step one done. We kind of know what is the thing that we want to be building. Now, step two is, does this have any security and privacy implications? And the answer is yes, right? Because if you think about what this system needs to do, the system needs to identify close contacts of positive people and then tell them to quarantine. So this system as a whole, even if you don't know how it's implemented, must embed social contact information. It must embed information about who interacts with who. So if you poke at this a little bit more, a couple of risks will immediately fall out. So if you have ever done any research into this type of systems, you'll immediately notice, okay, if that is the case, right, we should be very careful that we design a system that actually does not leak social interactions. And then one way of doing this close enough, long enough thing would be to capture location traces. So another risk that immediately pops out is, okay, maybe the system could reveal location traces, namely who is where when, which again is risky. And then the last one that immediately pops out is that, remember, you only want to do this dance of notifications when somebody actually tests positive. So there is some notion of positive individuals that must be baked into the system, then leading to a risk of identifying them. And I am assuming that most of you are upstanding citizens that are actually not so concerned about being identified as a positive individual, but there can be many scenarios in which being identified as the idiot that got COVID and then infected their relatives and friends can actually be extremely stigmatizing. So this is one that you need to be careful about. One of the downsides is that we figured out early on when we started thinking about these risks much more deeply than I have time to capture here, is that this risk is actually inherent to the function. The moment you ask, I need to receive a notification when somebody close to me was positive, that gives you information about who was positive. And the obvious example to see how that works is, if I only had contact with one person in the last 10 days and I get notified, then guess what? That person must have been positive. And it turns out that essentially any contact tracing system, regardless of how you implement it, has therefore a risk of identifying positive. Okay, good. So we did our sort of step one and of figuring out what is the thing that we should be building, namely notifying people. We did our step two, starting to figure out what are the privacy risks, and I captured a couple of them here. And now you might be wondering, Wouter, are you sure that these are real risks? right? And people in March, April, when of 2020, when we were writing about these things, right, we're really essentially throwing this at us, right? Like, you people are crazy. This would never happen in practice. Fast forward like a couple of months until sort of summer, fall 2020. This is what you get. So here are just a couple of examples of things that you can find in the news. In Germany, contact lists that were used to notify people that visited the restaurant were then used by the police for crime fighting. Definitely not the purpose for which they were collected. Contact tracing data, why not sell that, right? And finally, I mean, if you know who is this pretty guy on the terrace, right, you might also use that to harass people. Now, last but not least, right, a lot of these systems would make the claim, okay, there is this risk, the central party might do something or could do something, but this would never happen in practice, which is, for example, the claim that was made in Singapore, right? We know we have access to this data, but we would never use it, except that, of course, they did. So all of this goes to show that these risks are not just academic, right? They're actually real. They really occur in reality, and we should be designing systems that protect against this. By the way, I can really recommend this Twitter thread. It's a lot of fun in a kind of sad way. So in the next part of my talk, I want to be talking very specifically about proximity tracing systems. So these proximity tracing systems that you will have all in your pocket, and actually the one that I'll be talking about and the one that I designed is the one essentially that is in your pockets in CoronaWarn app, uses Bluetooth beacons as a proxy for distance between people, and then uses that to determine, okay, this person was positive, this person was close to the positive person, therefore they should be notified and subsequently quarantine or get tested. Okay, so that is the purpose that we're going to be talking about so far. Now, I'm going to do a relatively simplified version how this protocol works, because I actually want to be talking about some more interesting systems aspect of what happens when you actually start to roll something like this out. So here goes. So when phones that use this DPGT proximity tracing system, that is also in your phones, they will be using Bluetooth Low Energy to broadcast randomized beacons. These beacons rotate every 15 minutes, and they rotate so that people that receive these beacons cannot use them to track people as they move about in their lives. Now, whenever a nearby phone receives these beacons, right, and nearby really means 2 meters or something, they will write down this beacon in a list of scene numbers. And I want you to realize that really this list of scene numbers acts kind of as a representation of the social graph, but because these lists are distributed among different people's phones, there is actually not a central representation of the social graph between people. Now, this by itself, of course, does not let us do notifications. So how do we do notifications? We do notifications by telling phones, this list of beacons correspond to people that actually are positive. So how does that work? When somebody tests positive, the testing center or the hospital or the doctor will send them an upload authorization code. The user will enter that in their phone, and then their phone will upload 2 things to a central server. One is the list of beacons that this phone has been transmitting, together with this upload authorization code. The server will receive this, check this authorization code, ignore it if it's not correct, and then if it is correct, transmit this list of beacons, right? And this list of beacons really tells you, okay, each of these beacons on this list corresponds to somebody that was positive. In this case, all the same person, but when they go down to the other phones, this might be several lists of different positive people. Now, what the phone does is it will take these lists of beacons that were marked positive and compare them, essentially do an intersection with the list of identifiers that they have seen. Now, any overlap between that, right, means that this phone here saw a beacon from somebody that was positive, meaning that they were in close proximity. Now, when that happens, they do a little bit more computation based on signal strength and duration in order to determine, is this above a threshold to notify a person? But in a nutshell, this is the full idea. There are a lot of variants that one can make, for example, in how to make this upload a little bit more efficient, or how to deal with privacy risks in a little bit nicer. So let's go through these risks that we identified starting out. First of all, we were concerned about leaking social interactions, right? Because it's essential that these systems somehow capture these. But the way this decentralized system has been designed is that these social interactions are really captured in these lists that are only stored on individual. We were also concerned about location traces. Is it possible to track people? And again, because these beacons are randomized and change every 10, 15 minutes, tracing of non-positive people is not possible. Now, you might have noticed that on this slide, positive people upload their full list of beacons that they have been transmitted. So this kind of removes this unlinkability between different beacons, and it indeed makes it a little bit easier for receivers of many of these beacons to follow positive people along. Now, remember, positive people are relatively rare, or at least they were at that point, maybe currently not so much anymore, at least not in the Netherlands and not in Germany. But still, this is a relatively small set of the population. Now, there is this little asterisk here, which is a reminder for me to tell you that different sort of detailed deployment considerations or protocol considerations can make this a little bit more difficult or a little bit easier. But the fact of the matter is location traces just don't mix so well, because people just don't intersect so well in the places where they go. So typically this remains possible to some degree. Now, finally, because it is possible to some degree to trace people, this also means that it becomes a little bit easier to identify positive individuals. Remember that this is an inherent constraint. Any notification system doing contact tracing must, by nature of its functionality, enable people to identify who is positive. In this particular case, though, it does become a little bit easier. So that is fair. Now, what happened when we designed this system, right? This was early March, April 2020, when I was working a lot and not sleeping so much. We designed this protocol, and we designed this relatively simple protocol. And one of the reasons was, look, if you need to be fast and if you want to be on the market fast, you don't have the luxury of coming up with something very complicated. Also, simplicity is very good in the sense that it also makes it very easy to figure out what the weaknesses are in ways that competing designs that were proposed around the same time really are not. Like, simplicity really is a key factor in making things easy to analyze. Now, we were not the only ones that liked our simplicity, right? So what happened in the end is that Google and Apple, sort of the end of April 2020, decided to adopt essentially our design into their Google and Apple exposure notification framework. Right, so everything I was telling you about is something that we proposed early on March, April 2020, and that was integrated into Google and Apple. And this is now the thing that runs inside Corona Warn app, inside Swiss COVID app, a total of 40 plus countries, and being used by, my rough estimate, more than 100 million people. Good. So that's pretty cool. So we designed this protocol got deployed all over the place. Now, what I want to introduce to you next is one of these funky little arrows in my diagram at the beginning, namely that the way you deploy things matters, and that just the cryptographic protocol by itself is not necessarily enough. So let's look at one of these funky little protocol things that actually the Google and Apple exposure notification framework does not say much about. So when this user tests positive, right, they make this upload to this central server. And the question that you should ask now that you have this design is, does that influence my security and privacy risks? Turns out that yes, it does, right? If you're concerned about a network observer, for example, the network operators at your university, your ISP at home, maybe your mobile network operator, all of these will be able to see this upload to the central server, and all of them will be able to conclude, oops, Wouter is positive. Now, this can be solved At least according to the DPTT design paper, this can be done in about 5 lines. Actually, really 1 line. This can be mitigated using dummy uploads. Okay, let's see how to do this, because we were, I think, a little bit optimistic about how easy that was. So what the property that we really want when thinking about this type of uploads of keys and protecting them against network observers is a property that we typically call deniability, in the sense that the user should be able to deny being COVID positive. They should be able to say, well, you might have seen something that looks like an upload, but I'm doing uploads every day. And so you really cannot conclude that I am positive. Or there is another benign explanation why that can happen. Or turning this around, which is essentially saying the same thing, but from another perspective, given what the network observer can see, they should not be sure about whether the user really uploaded their tokens or not. Now, this is a very fluffy way to capture this. In our analysis, we actually make this much more precise. And really the key to this mathematical analysis is to try and compute this quantity, namely the probability that given the network observer's observation, the user is actually positive. And we want this probability to be small. So this means that after the network observer sees this observation, the posterior probability of the user being positive, which is this entire thing here, should still be small, meaning the network observer has a lot of remaining uncertainty. Now, when you're doing this type of thing, right, like I'm just writing here observation, but really you need to be precise about what that means. So if you think about network traffic and you think back to your network class, right, even if this traffic is encrypted, this means that this network observer can see destinations, namely this server, can see if there are multiple connections, where they go. It can see timing between them, and it can also see payload sizes. So all of this is even possible, even if you have TLS in place, etc. So you do all the normal things right, you're still stuck with all of this. So how do we solve this? Solving this is hard. So typically, when you write an academic paper, you say, look, I kind of know when real uploads happen. I have some distribution, and that is what I'm going to use to design my system. Now here, in this case, we have no clue. We don't know what users do. We don't know when they get notified that they have COVID. We don't know when they get the codes, and we don't know when they actually do these uploads. Making matters worse, obviously, we also cannot remove these uploads, which will solve the problem, because then the system stops working, and we can also not delay them, because that will then delay subsequent notifications. So the key idea that we designed in order to protect against this is this idea of doing dummy uploads. So every now and then, following a Poisson distribution, the phone will make an upload that looks exactly like a real upload. And it will do this in our configuration once per 5 days on average. But really, these parameters depend both on how many positive people you have and other sort of design considerations. Now, this turns out to be very difficult in practice. So we found a bug in the Spanish implementation that essentially scheduled dummy uploads completely wrong, which they fixed. We got a nice CVE out of it. We also caught probably more than one error in Swiss COVID, one before it came out, another a little bit later. And we have been recently looking at some other implementations, and our preliminary conclusion is, unless you happen to have talked with us, you're probably doing this wrong. And just to get you a little bit of an idea of why this is so difficult to do, I want to very quickly run you through an example of what actually happened in Swiss COVID. So for ease of deployment and for ease of software development, there is actually not one server, but 2. And for users to be able to do this upload, first of all, the testing facility will request an authorization code to this COVID code server managed by different people than this one. Send it to the user will enter it in their phone, and then the phone will make 2 requests. One to the COVID code server to post this authorization code and get something nicely cryptographically signed back, and then we'll do the final upload. So what does this mean for dummy traffic? Now remember, dummy traffic must mimic real uploads. Now here is a graphical representation of what a real upload looks like. Request to COVID code server, boop, request to key server to do the final upload. Now, in order to make dummies that mimic all of these, we really need to do the same bloody thing, right? So we really need to do request to COVID code server, request to key server. And really implementing all of that is pretty tricky, at least implementing that correctly. So just to wrap up this part, right? Like this DPTT design was adopted widely, 40+ countries, more than 100 million users. And we've seen that there's sort of two aspects that play a role here. One, you need to do careful cryptographic design of your protocol. And then you need to think really about, okay, now once I'm deploying this, what does that mean for my end-to-end security and privacy? Now, I skipped over a lot of cool details. So if you're interested, this GitHub repo has a lot of them, or drop me an email about that. Okay, that's the first part of my talk. Now, second part of my talk, we figured out that this proximity thing is nice, but we really also need a system that does notifications when people have been in the same space. So following the same process, talking with contact tracers, talking with APIs, etc., figuring out, okay, we're going to do something very similar. We're going to notify people that shared an indoor space with people that tested positive. And then as a side effect of these conversations, a couple of other sort of functional and kind of non-functional requirements popped up. Namely, first of all, health authorities wanted to be in the loop, which was new, because they realized the risk of being exposed in a restaurant where everybody is seated and you have table servers is a heck of a lot lower than being at the salsa bar in the middle of the night in the basement of the building where there is no ventilation. Okay, so these things matter. So this is why they wanted to be in the loop to determine where to send, for which locations to send notifications. And then finally, it should be relatively easy to do rollout, because otherwise people get very cranky. Now, remember step 2. Does this have any implications for just this requirement to do notifications based on locations? Does that have any implications? And the typical thing that people want you to think about when thinking about these things are like bars and restaurants. But what about religious buildings, church, mosques, activist meetings, political gatherings, meetings for specific communities and support groups? All of these, much more than the ones here on the left, really directly impact freedom of movement and freedom of association. Now, you might argue, as people argued to us, really it's the ones on the left, and we would never do these things on the right. In fact, that is what happened when we were in nice conversation with the developers of the Luca app, which I'm sure most of you know, where they told us, and I'm going to paraphrase here and not try and butcher the German too much, right, that political gatherings, religious buildings, etc., the use of Luca is voluntary. Okay, kind of makes sense, except if you look at the law, for example, from Mecklenburg-Vorpommern, essentially says for each of these, plus a whole boatload more, sorry, but using Luca is voluntary. So taking these things into account actually doesn't. So this gives us now 2 new risks that we identified. One is we have a bunch of locations that are by themselves sensitive, and locations that by themselves might actually not be found in any database, right? Think of community meetings, for example, that you cannot just Google, where's my local eco-activist group meeting? Probably doesn't, right? So there is no database for that. And we wanted to make sure that there would not come one. And then now you're in a situation where a lot of data is being linked potentially to locations, namely, you know, this latest infection happened at Wouter's bar. So this is like definitely a bad place. You should never ever visit them. So that's one aspect. Now, the other thing is that we're storing information about users' visits to locations, where before we were storing somehow a representation of who they interacted with. Now we're storing information about locations. And again, you might be realizing that this would be interesting data for law enforcement to figure out where the latest suspect went, but also, for example, for abusive partners to figure out where the abused person in this relationship went, right? So if you make these systems mandatory, one needs to think about all of these things. Now, when we were designing this system, we took a lot of easy, quote unquote, design choices. as you probably have guessed, like essentially any other system in this space, we decided to use static QR codes that users scan with their phone when they visit. This phone will store, following the decentralized paradigm of before, a record of this visit on the phone. Then health authorities will figure out by some magic process, talking with people, for example, that there was a case at one of these locations, and that will trigger notifications, potentially together with the location. Then finally, phones receive some of this information, will do a computation, and then notify their owner. Good. Now with this in place, we actually get rid of a whole boatload of these. Okay, health authority in the loop, check. Easy deployment, printing a QR code, probably check. Privacy of locations, at least we don't need a new database. We'll need to deal with stigmatization. I won't have time for that in this talk, but it's something that one needs to take care of. And then finally, privacy of visit. So remember, one of these arrows in my big diagram says, once you settle on a specific way of building something, that might introduce new risks. Now, in this case, because these QR codes are fixed, right? They're pasted on a door and they're not being changed every 2 hours. We might need to consider attackers that actually know these QR codes. Okay, so let's build a system that tries to tackle primarily this thing. So we want records on the phone and they should not reveal to which location they belong. Now you might be like, I know something. We're going to use encryption. So let's use that as a strawman design and see what we get. So how would you use encryption in this case? A location owner might, for example, generate one of these QR codes, put in there a public key for which they have the private key, as well as a description of a location. The visitor would scan this QR code and then store an encrypted record on their phone. And this encrypted record is relatively simple. Once they leave, they're going to encrypt the entry and departure time against this public key that corresponds to the phone. Good. Seems reasonable. Hopefully this gives us some privacy. Next step, how do we do notification? So let's fix functionality first. Remember, at some point, public health officials will determine, there was a case at this location. They will request the private key and then publish this private key together with the time slot that actually this positive individual was there. Phones can receive these private keys and then they can do kind of the obvious thing, right? They take one of these records, they try to decrypt it with the private key that they just got. If it decrypts, you have the time that the user was there, the time that the positive person was there. If there is overlap, you need to notify the user. Great. At least it works with something, but there are some caveats, which is why this is a strawman design. First of all, when you reveal this private key, this doesn't just open the records that roughly correspond to the time for which you actually wanted to send notifications. No, it will open all of them, right? And remember, these things are pasted on a door, they never get updated. So this is like several months worth of records that now become easily decryptable by our attackers that might have access to these records, okay? So that's not something that we wanted. So how do we solve this? So we decided to use identity-based encryption. And if you don't know what is identity-based encryption, think of this as a very cheap way to pack a whole boatload of public keys in here, one, let's say, for every hour, okay? So boatload of public keys, and we're going to encrypt now against the time that we're actually there, okay? Good. Second one, if you actually decide to do the privacy proofs for this, which is what we did, turns out that your typical CCA or CPA security of encryption does not get you the properties that you want, because you want to hide not just the plain text, but actually which public key you have been encrypting against. So we need a much stronger property of privacy of ciphertext, or in the case of identity-based encryption, privacy of both the identity, which we'll later see will be the time, as well as the authority, which corresponds to the venue that created it. Now, finally, you might notice that these things are like completely independent, which makes for nasty attacks that I won't have time to go into, where you take the public key of a place that might get a lot of notifications and put a description on there for something benign, trying to trick people into getting notified way more often than they should be. Good. So let's put all of this together into the final system that we designed. Setup, not particularly surprising, more or less as you were expecting. every location owner will generate this entry code that will post at entrances or tables, which will contain description of the location, a nonce, because nonces are cool, and a private key, a public key corresponding to this identity-based encryption scheme. Then they also have, of course, this private key corresponding to this public key. Now, this private key, they keep private in a QR code in their desk drawer. Good. By the way, I can read all the chat. And probably everybody else. Good. So now that we have this setup done, we have these two QR codes, and we need to figure out what do users do. Users do kind of the obvious, right? The same thing as we did before. They scan this entry code. They will determine, first of all, when do they leave? So they scan this code, take the content, wait until the user leaves, and then create encrypted records. And they will encrypt records for every time slot that overlaps with their visit. And for each time slot, they will compute, for this identity-based encryption scheme, an identity that corresponds to this time slot, as well as to the description of the location. And this will fix this problem where people could substitute public keys from other places by binding it really to the location. So we compute this identity that is time and location based, and then encrypt against this identity under this master public key. Now, if you were like before, what the bleep is identity-based encryption, think about just encrypting against one of this long list of public keys corresponding to the specific time. Usable store, entry, and departure time as before. Takes all these records, put them on the phone. Cool. Now, how do we do tracing? Tracing kind of in the obvious way, right? Health authority figures out where is the case, contacts the location owner will scan this second QR code that is in their desk drawer, and then their device will compute decryption keys that correspond really to the time slots for which we need to send notifications. So how does it do that? It will recompute these identities, then use the typical IBE trick to compute the corresponding decryption keys, upload all of this to the central server. Central server will do some simple checking to make sure that this is indeed for the location that they wanted, and then send it to all the phones in the system. Now, these phones will take these identities, will take these private keys, do trial decryption. If decryption works, they will notify the user as before. Whew. Okay, that is how you do this with identity-based encryption. And really, we needed to add here quite a bit of crypto machinery and quite a bit of proofs in order to make all of this work and tie together. Now, you might be wondering, Wouter, but you want to do practical stuff. Does it really scale? So we did some experiments. So we ran it on a couple of phones, and especially this trial decryption step takes about 3-4 milliseconds on older phones and Android phones for some reason, is much faster on iPhones. If you take a reasonable configuration, we can debate that. That will take around 5 seconds per day in order to process. I would say that's pretty reasonable. You can do some other tricks in order to make this faster if you really need to. But this really still already requires contact traces identifying 50+ locations per day, which in my experience, they have never done. So to wrap up, this presence tracing thing called CrowdNotifier was also deployed in Swiss COVID, which has 2 million active users. This was a slightly different variant. We wrote a big text spec about this, describing both this variant that we did implement as well as the original one that was in the PETS paper that has all the proofs and analysis. If you want to know more, this GitHub link is the place to be. So in the last 1-2 minutes, I just want to wrap up this talk and tie a nice bow around this. So I've described to you 2 systems for doing contact tracing, one based on proximity, one based on locations. Both of these have been widely deployed, right? The proximity Bluetooth one in a lot of countries, the latter one essentially in all of Switzerland. And really these depend on a very careful analysis of requirements, risks, and the constraints that come from practically deploying these systems. And you really need to look at all of these layers in order to figure out how to build these in a privacy-friendly manner. And then last but not least, for both of these, we benefited a lot from an open design process where we got a lot of feedback from different people, for which I'm very grateful. This is also a great point to thank my 40+ collaborators that worked with us on several aspects of these, and without them, this would not have been possible. And then finally, on a little bit of a more bummer note, none of this tech will actually help you unless it's used by your population and integrated with public health authorities, which is actually much more difficult than it might seem at first glance. So just to wrap up, last slide, right? I hope this gives you a little bit of an idea of the type of work that I do in designing for privacy-friendly and purpose-limited systems, which really requires figuring out what should we build and knowing what can be done in terms of privacy-enhancing technologies, figuring out which risks are there and how to mitigate them, then figuring out how to solve these risks using new building blocks, and figuring out what extra constraints come from trying to deploy all of these. Now, all of these are hard. I hinted at a couple of papers that we already wrote. We should have wrote probably a couple more, 1 or 2 are in the pipeline. I'm happy to take any questions for you. It was a pleasure.